So next we will discuss how we can extend the concept to bivariate random variable to multivariate random variable setup. So if you have understood clearly that how we discussed or we extended this concept from univariate random variable to bivariate random variable cases, then very straightforward way, analogously, we can extend. Instead of 2, we will just discuss n number of random variables. So in nature, this n number of random variables is very important, because many random phenomena we cannot just explain using only one random variable or two random variable. We need multiple random variables. We will discuss, and in that case, multivariate random variables in the next part. In many cases, we come across the situations where if one random variable cannot explain a particular random phenomena properly, we need to consider more than one random variable. For example, if you want to describe a pollution, so pollution, air pollution, suppose we are considering air pollution. So air pollution, just if you want to consider the amount of particular air pollution, for example, particulate matter PM 2.5 or PM 10 or carbon monoxide, these are not enough. Only one random variable you cannot explain it. You need to consider more than one random variable. So explaining many quantities like amount of carbon monoxide in the air, amount of carbon dioxide, amount of nitric oxide, like here it is, you can see that SO2, SOx, PM 2.5, PM 10. To explaining that, so like here greenhouse effect, particulate contamination, we need to consider more than one variable to explain this phenomena. So multivariate responses are found in many fields in the social and natural sciences, clinical trial, placial experiments, ecology, econometrics, epidemiology, etc. For this reason, we need to extend the concept of bivariate random variable to any n number of random variables. So here this extension very straightforward. If you have understood bivariate random variable, here we will discuss how to extend it to bivariate random variable to multivariate random variable cases. Let first discuss the bivariate random variable cases. Let xy be a bivariate random variable. So how it was defined? So S, for a random experiment, we have a sample space S, and bivariate random variable is defined by a measurable function. Xy is a measurable function. For each S, we will find this is a R2, so element, so S, so you will find a point in R2. So it is XS, YS. So this is a vector in R2. So XY is a bivariate random variable. It is a function. It is a function from S to R2. So that each element S belongs to S. It is a measurable function. There is a element in R2. For let us consider, instead of xy, because we want to extend to n variables, so let us consider x1, x2. It is a bivariate random variable instead of xy. So this is nothing but a measurable function S to R2. Now we'll extend this bivariate random variable concept to n variate random variable. Let x1, x2, xn be a function. So function from a sample space, so it will be a measurable function. Let x1, x2, xn be a measurable function from S to R, S to Rn. So like x1, x to xn, S to Rn. So for each element S belongs to S, x1, x2, xn of S is nothing but defined by x1s, x2s, xns. Here each x1, x2, xn are random variable in random variable. So we can define like bivariate random variable, we extend it given an experiment n tuple random variables. x1, x2, xn is called a n-variate random variable or n-dimensional random variable if each xi associate a real number with every sample space S belongs to S. Thus an n-variate random variable is simply a rule associates an n tuple of real number with every S belongs to S. So basically each xi is a measurable function, S to R is a measurable function. Then if you consider the n tuple, like we can, so here for simplicity we write, but is a vector, we write as a column. So x1, x2, xn n tuple is called it is called a n-variate random variable which is a measurable function which is a measurable function from S to Rn is a, you know that this is nothing but R cross R cross R n times. So like it is extension of R2 and n is a natural number, where n is a natural number, n can be 1, 2, 3. If it is a 1, then it is nothing but one single random variable. 2, it is bivariate random variable, and more than 2, it is 3 is trivariate random variable. For any n, it is n-variate random variable defined as we just now we told. So this is x1, x2, xn. So we can denote like it is like x tilde, it is a vector, it is a measurable function S to Rn defined by S to Rn, sorry, defined by x tilde of S is equal to, so nothing but it is x1, x2, xn of S. For S belongs to S, it is x1s each xi is a random variable for I is equal to 1 to n. So this is a random variable. So xy will be a real number. So x1s will be real number, x2s will be real number, xns will be real number. So this vector will be in Rn. So this is a measurable function from S to R. Now analogous to the very similar how we defined the bivariate random variable, bivariate distribution function, here we will define the multivariate distribution function. So this the n-variate cumulative distribution function. So here it is also it is mentioned x1, x2, xn n-variate random variable, then the joint CDF cumulative distribution function. So let us write in this way, let let x1, x2, xn be a n-variate random variable. So for simplicity let us denote like this. So let x1, x2, xn, let x1, x2, xn be an n-variate random variable, let x1, x2, xn be an n-variate random variable. The joint CDF cumulative distribution function, it is a multivariate distribution function of x is given by, so it is defined as, is defined by, is defined by, so you recall that how we define the bivariate random variable, f of xy of small y, probably that x less than equal to x, y less than equal to y. So if you replace y by x2 and x by x1, then it will be x1 x2. So this will be x1 is less than equal to x2, and x1 x2 is less than equal to x2 is x2 is less than equal to small x2, where x1 is belongs to real number, x2 is belongs to any real number. So this is we define. So you want to just similarly we will define, we extend it to the n variate random variable. So it is this, if you have understood the bivariate cases, the n variate cases will be very simple. Just you just extend it to n variate defined by f of x1 x2 xn, x1 x2 xn. This is probability of x less than equal to x1, x less than equal to x2, x less than equal to xn. So we know that all are even and common, nothing but it is a intersection, because you know this is probability of x1 less than x1 intersection x2 less than equal to x2. So this is, probability of x less than equal to x1, x less than equal to x2. So this is the joint cumulative distribution function x1 x2 xn. This is defined like this. Now the similar to the bivariate cases, here also some of the properties are there, but we will not discuss, it will be a little complicated. So we'll discuss some of the important properties. So bivariate cases we discussed most of the properties. It is right continuous, because it is a probability distribution function, it is a probability. So one of the simple, that this is x1 x2 xn, this will be less than equal to 1, greater than equal to 0. And what will happen if you do that, one of the variable tending to infinity, or all the variable tending to infinity, limit x1 goes to infinity, limit x2 goes to infinity, limit xn goes to infinity, all variable goes to infinity, f of x1 x2 xn, x1 x2 xn. Note that like earlier in bivariate cases, whenever you are tending to x1 goes to infinity, so like all it will be tending to S, it become whole sample space. So this is nothing but probability as S intersection S, nothing but probability of S, this is 1. Now if he one of the, so formal proof we will not do, just to understand it like this, that x1 goes to infinity, all event go become a certain event. So so just we can, so just we can just directly write that this is nothing but equal to 1. So now how, if you can show that probability, so now if you, one of the variable, any ith variable suppose goes to minus infinity, so then x1 x2 xn, other variable x1 x2, suppose this is ith variable xn. So now one of the ith variable, suppose x less than equal to xi. So if xi goes to minus infinity, this tending to null event phi, so then any whatever the event intersection with null, this become probability of the null event, so this becomes 0. So it is just very similar to the bivariate cases, all the properties. So now whatever useful we will discuss, whatever we will utilize in the future. So some of the concept, how we will get the marginal probability distribution functions. For example, marginal probability distribution function, now for bivariate cases, suppose x1 and x2 a bivariate random variable, so x1 and x2, then in that case marginal means subset of the random variable means x1 or x2. So now these are the proper subset, so because that only we want to find. Now if you take three variable, then any subset of the random variable may be x1 x2 x1 x3, maybe two containing two random variable x2 x3, like one random variable x1 x2 x3, these are all subset of this. If you take the how many subset you can consider proper subset, so then these are the subsets. So then any subset of this random variable, if you want to find joint distribution function of that, then it is known as the marginal distribution, we say. Now how to find that? Suppose if you want to find, we have the joint probability distribution function x1 x2 xn, and you want to, this is known to us for n random number of variables. The joint probability mass function is known to us for any value x1 x2 xn, and this is known to us for any value between Rn. x1 x2 xn belongs to Rn. Now we want to find marginal probability mass function of only x1 x2 xn minus 1. This is one subset. So we are interested to know x1 x2 xn minus 1, xn minus 1, and the we are not interested about the nth random variable. We are just want to know the joint probability distribution function of x1 x2 xn minus 1. Now how we can find that? So note that this is nothing but probability that x1 is less than equal to x1, x2 is less than equal to x2, and xn minus 1 is less than equal to xn minus 1. Now this is, if you include, this is all intersection. If you intersect with s, then also this is same, this probability will be same. So this is same as, we can say that this probability say that same as limit this probability that xn variable tending to infinity, probability that x1 less than equal to x1, comma x2 less than equal to x2, comma xn minus 1 less than equal to xn minus 1, comma xn less than equal to xn. So this nth variable, if xn goes to infinity, then this become almost certain s, the certain event s, the sample space s, intersection with s become the previous these things. So this is nothing but limit xn goes to infinity f of x1 x2 xn joint cumulative distribution function x1 x2 xn. So the n minus 1, the joint cumulative distribution function up to x1 n minus 1 is nothing but nth variable tending to infinity joint cumulative distribution function of x1 x2 xn. So similarly, if you want any subset, you just, so it is you can remember that bivariate case also, if you want the marginal distribution of one variable, then you have to take the limit of the n goes to, that variable goes to infinity of the other variable. So now for in general cases, if you want any subset, suppose alpha 1 alpha 2 alpha some maybe you take a notation like u, suppose this is a subset of the values this 1 2 up to n, suppose this is particular some subset, and you want to find f of x alpha 1, x of a alpha 2, x alpha u. So x of alpha 1, x comma x of alpha 2, x alpha u. So whatever you have to, what you have to take, so whatever the remaining value, you have to take the limit goes to infinity. So we cannot notationally, it is very difficult to compute. So just particular cases we can discuss. For particular cases, suppose here we have discussed that x1 x2 xn minus 1 we did it. Suppose you want to find just one variable f of x1 of x1, so then nothing, this is how we will find that this joint probability distribution function given to us. Then how you can find the marginal probability distribution function of x1? So this is nothing but, if you take the limit the other variable tending to infinity, limit x2 goes to infinity, x3 goes to infinity, take the limit xn goes to infinity, f of x1 x2 xn x1 x2 xn. If you take the other variable goes to infinity, then you get the marginal probability distribution function of x1. So similarly you can do for suppose other example, suppose you want to find marginal distribution function of f of any two random variable like xi and xj, I not equal to j, obviously xi comma xj we want to find. So then what we'll do, the limit x1 goes to infinity, limit x2 goes to infinity, then limit x I minus 1 goes to infinity, then limit x I plus 1 goes to infinity, limit xj minus 1 goes to infinity. So basically the other variable other than the I and j, limit xj plus 1 goes to infinity, limit xn goes to infinity, So f of x1 x2 xn, x1 x2 xn. So other than the ith and jth variable, so you have to take the limit in goes to infinity, then you will get the marginal cumulative distribution function. So hope you have understood this concept. We'll discuss, this is because it is very similar extension, so I think here it is represented. So in these are actually, you cannot write this, infinitive is not a real number, you cannot put and get the value, it is a notation only. You have to take the limit at x1 goes to infinity, x2 goes to infinity, xn goes to infinity. So here you can see that the marginal cumulative distribution function, it is found by, here it is, they have replaced the value infinity, but we have to take the limit. That's why it is like setting the approximate xi goes to infinity. So similarly, x1 x2 you want to find the remaining variable, you have to take the limit as x2 x3 goes to infinity, x4 goes to infinity, xn goes to infinity. So this is some of the important properties. Now suppose how we can say that x1 x2 xn are independent random variables. So here like bivariate cases, if you can write the joint cumulative distribution function as a product of their marginal distribution function, then they are independent random variable. Here also, for if x1 x2 xn are independent random variable, then joint probability cumulative distribution function x1 x2 xn can be written as their product of their marginals, f of x2 f of xn xn. So that means we can write in short notation, I is equal to 1 to n f of xi of xi. Then we can say that the x1 x2 xn are independent random variables with respect to the distribution function. Now next we will discuss what if all the random variables are, suppose, discrete random variables, x1 x2 xn are discrete random variables, then in the bivariate case we discuss the joint probability mass function. So here we will discuss also joint probability mass function if x1 x2 xn are discrete random variables. So if x1 x2 xn are discrete random variables, the invariant random variable, so invariant random variable we denote x1 is a discrete we say, so we give the name invariant sometimes, or sometimes we say the name is that n-dimensional invariant random variable or n-dimensional random vector. So it will be, so we can say that x1 x2 xn is a discrete n-dimensional random vector, or invariant discrete invariant random variable also a random variable vector. So in that case we discuss the probability mass function. So you can remember that for joint probability mass function we define for two random variable xy, this is nothing but probability of, so we wrote xi yj, so x is equal to xi, y is equal to yj. So similar to here, so here we replace xy as x1 x2, so then we can extend it to n number of random variables. So the joint probability mass function of x, x1, x2, xn is defined as p of x1, x2, xn, x1, x2, xn. This is nothing but probability that x equal to x1, comma x equal to, sorry, the random variable capital X1, it is taking the value small x1, random variable capital X2, it is taking small x2, like xn taking the value small xn. So this is the probability that x1 taking value x1, x2 taking value x2. So this is the joint probability mass function. Now you may remember that in bivariate cases how we can find the marginal probability mass function. Suppose we know that we have this joint probability mass function, it is known to us. Now if you want to find the marginal probability of x, then we have to take the sum of the other variable. Then all the possibilities we can consider that xi, fixing xi, it can take the probability that other value it can take. So now if marginal probability mass function of yj, also similarly if you have to take the sum of the other variable fixing yj. So here also if you want to find the marginal probability mass function of suppose x1, suppose any subset of the random variable, suppose n minus x1 x2 xn minus 1 marginal probability mass function you want to sum. So then the marginal probability mass function here it will be joint probability mass function, because it may not be a single variable subset may be contain more than one variable. The marginal joint probability mass function of x1 x2 and xn minus 1 is given by so p x1 x2 xn minus 1. Suppose this is known to us for all x1 x2 xn. Now we want to find the this subset. So this particular subset, any subset we can find. So this is, then we have to take whatever we consider this variable here and whatever we did not consider, we have to take the sum of the possible values of this variable. So this is xn taking some value, some range of this x1 x2 xn. So then x1 x2 xn, x1 x2 xn. So this is x1. So this if you want to find, so now if you want to find suppose the only x1, so suppose any ith variable suppose you want to find. So suppose for in particular suppose marginal probability mass function of x1 you want to find, that is nothing but probability of x1 equal to x1. In that case you have to take the sum of the other variable. So this is sum of x2, sum of x3, sum of xn, p x1 x2 xn, x1 x2 xn. So for any ith variable suppose you want to find, so then this is nothing but x1 xi minus 1 xi minus 1 xi plus 1 xn, p x1 x2 xn, x1 x2 xn. So any marginal distribution function, if you want to find whatever the subset you are considering, then the remaining variable you have to take the sum of this joint probability mass function. So just we want to write suppose x1 x2 we want to find this subset. So then x1 x2, then the remaining variable we have to take x3 x4 then this is xn, probability x1 x2 xn, x1 x2 xn. So this is I hope you have understood now like how we can find the marginal probability mass function from the joint probability mass function. So we did not discuss the properties. So properties are very similar to bivariate cases because it is a probability. So then this joint probability mass function will be x1 x2 xn will be always greater than equal to 0. And now suppose you want to find the cumulative distribution function from this joint probability. So the joint CDF, the joint cumulative distribution function of this vector, random vector x1 x2 xn is can be found is given by so this is f of x1 x2 xn, x1 x2 xn. So this is nothing but probability that x1 is less than equal to x1 comma x2 is less than equal to x2 comma xn is less than equal to xn. So this is nothing but you have to take the sum of the probability mass function up to the value x1. So this is nothing but how we can represent. You have to take a variable. So like how we can represent this. So we have to take the sum of all the values xk. So here actually the problem is that this notation problem. So we have to take some different notation to understand it. So let us see that what the notation followed here. So this is only properties, this properties it is discussed. So this is not discussed here. So another property is that the sum will be equal to 1. So that is very obvious, because it is the probability mass function. So if you take the sum of all x1 x2 xn p of x1 x2 xn x1 x2 xn, this sum will be is equal to 1. This is the another property, this is the second property. And the third property, it is not mentioned, just I just want to represent. So basically we have to consider all the value. So let us denote this value. Suppose you consider this variable u1 u2, just because it is a variable. So this is this value taking the value u1, this is nothing but u2, and this is nothing but un. So then all the value x1 less than equal to u1, less x2 less than equal to u2, all the value this probability mass function can is non-zero, and xn value less than equal to un, then you have to take the sum of this probability mass function and all the at the value x1 x2, all the value x1 x2 xn. So we have understood it. It is just a extension from the bivariate case to multivariate case. Just I am writing it. It is very straightforward. I hope you are following it. So next we will discuss the joint probability density function whenever the random variables x1 x2 xn are continuous random variable. In this case we need to discuss joint probability density functions. So next we will discuss the joint probability density function and the properties, and some of the properties, and how we can find the marginals. Now only we will complete here the joint the what is the how we can find the independence. So with respect to the with a discrete random variables. So if x1 x2 xn are independent are independent random variables, then in x1 x2 xn are independent discrete random variable, independent discrete random variables. So then if x1 x2 xn are independent discrete random variable, then the joint probability mass function x1 x2 xn x1 x2 xn, it will be nothing but basically this is nothing but probability that x1 is taking value x1 intersection x2 is taking value x2 intersection xn is taking value xn. If they are independent events, so then this will be nothing but their product, x1 is equal to x1 into probability that x2 is equal to x2 into probability that xn is equal to xn. So this is px1 of x1, px2 of x2, pxn and xn. So note that here capital X1, capital X2, xn, capital Xn are random variable. These are all measurable functions from X to R, sample space S to real number, set of real numbers. But small x1, small x2, small xn are some of the real numbers only. These are the some of the notation you have to follow, and then this can be in a short form. We can write I is equal to 1 to n pxi of xi. This is in this way. So next we will discuss the continuous random variables, how the multivariate random variables, in variate random variable we can consider all are x1 x2 x are continuous random variable, how the joint probability density functions will be defined. It is very similar to the bivariate cases, it will be extension of the bivariate cases, and joint probability density function, their properties and all, and when it will be independent. So we will discuss, and that also this will be for all x, this will be true for all x actually, that we have to mention for all Rn. So it is not that particular values of x1 x2 xn. If they are independent, then it has to be true for all x, that x1 x2 xn belongs to Rn.